With the rise of space exploration in the 22nd century, the need has arisen for complex space robots capable of completing sets of complex tasks to assist in exploration and territorial expansion. The Dharn Astrobot is able to, with an automated launch, clear moon rocks around any lunar module, while also deploying sensor decoys and deploying a flag on top of the lunar ridge, while also egressing the arm for flag deployment. Here you can see what the Dharn Astrobot will be competing on. In the center you can see the lunar ridge, and surrounding a lunar module in front of the lunar ridge are 3 moon rocks, which the Dharn Astrobot clears. To design the Dharn Astrobot, we first took to the customers. In a house of quality, we identified key customer requirements for our robot. Some of these include running autonomously, fitting within a standard box size, and being able to complete all tasks mentioned previously within a 40-second time limit. After taking into consideration key customer requirements, we developed a specification sheet to show everything that we needed to consider. Some of the most important specifications were to score over 150 points, place the flag in Zone 1, and fit within the standard box size. The reason why we identified placing the flag and fitting within the box size as some of our most important specifications is because the highest number of points are scored after flag egress, with a total of 88 points, and placing it in Zone 1, and we would disqualify if we didn't fit within the standard box frame. After identifying every specification of the mission, we took to the customer requirements to develop a function tree so that we could map out every function the Dharn Astrobot needs to complete. Some of the most important functions related to the most important specifications include transporting the flag. So we developed 4 sub-functions for transporting the flag: approaching the area center, holding the flag, transporting the flag, and releasing the flag. After developing our function tree, we used the low-level functions to develop a morph chart so that we could take it to the drawing board to implement ideas for how we would complete said functions. We concluded, after much debate, approaching the area center would be treated with tilted linear slides, holding the flag would be held in a tube, and releasing the flag would be released through a trapdoor. Around picking the most effective designs, we kept in mind the mantra, simplicity leads to reliability. We designed our robot so that we minimize the number of points of error inside of our robot by reducing the amount of mechatronics components. The Dharn Astrobot only has 2 motors and 1 long arm switch to complete all of the tasks. We named our robot's design Showing the Ropes because it includes a string and spindle system to deploy the flag. To start, our robot initializes by rotating the rock clearing arm to release our drawer slides. Simultaneously, as the mechanism deploys itself, the rock arm spins so that it can get into position to clear all the rocks. As if it stayed in its initial position, it would hit the moon rock sitting in front of the lunar module and displace the lunar module. After some time clearing the moon rocks around the lunar module, simultaneously our flag arm deploys partially, but it waits for decoy deployment. Once the long arm switch has deployed and decoy deployment starts, the moon clearing arm continues to rotate to fully deploy the arm and place the flag on top of the lunar ridge. As the decoys are being deployed, simultaneously, the motor responsible for decoy deployment retracts the arm backwards after release, and the rock clearing arm finishes rotation in the opposite direction to fully egress the flag arm. But before we could conclude on this final design, we also kept in mind some concept alternatives. Here you can see the Kickstarter, an alternate design that we created that involves wheels. Positioning for this design is critical because if any positioning is off, the device could deploy and hit the lunar module, which would cause a loss in points for our team. A pneumatic piston kicks the ground and deploys our robot on free spinning wheels. The frame pushes moon rocks away, and the sensor you see here deploys decoys at a timed interval. A flag is placed using drawer slides and a rack and pinion gear system utilizing the other motor. The same motor is used for reversing the drawer slides. Another design we came up with is the rock trap. A similar frame is used in this design, and our initial trigger starts with a solenoid. Solenoid releases drawer slides, which deploy the mechanism, and moon rocks are cleared using mouse traps. Positioning is critical for this device because if any slight movement in the wrong direction, the mouse traps will not be able to clear the moon rocks around the lunar module. A solenoid releases sensor decoys based off of starting position, with a timer set within the MyRio. And the flag is deployed using a motor directly connected to the flag arm. Arm is egressed by reversing the motor direction. To compare our designs, we used a first level evaluation matrix, with the Kickstarter being our datum. We noted that showing the ropes design had significantly much higher improvements in all factors over the rock trap and Kickstarter design, as shown in our third level evaluation matrix. Some of the most important distinctions within each of these designs that really set apart showing the ropes is being able to deploy the flag and egress the flag efficiently and effectively every single time. The Kickstarter and rock trap design were a bit iffy. The Kickstarter design didn't have much force to egress the arm, and so a rack and pinion method may not have been as effective. In addition to this, the rock trap arm, although being directly connected to a motor, has shown trouble in deploying the flag arm, as the weight can add too much strain onto the motor. Overall, we placed 12th out of the 23rd teams, even though we were seeded as 21st. Some of the issues that we ran into during the final competition were censored beacon alignment, as well as rocks having too much friction on the lunar ridge, so we couldn't fully clear, and it jammed our rock clearing arm. Because of this, our flag didn't deploy, and we lost a lot of points for that. Overall, even though we developed with the mindset of simplicity leading to reliability, our interconnected solutions ultimately led to our downfall. We learned not to create too much dependency between systems for missions and critical tasks. And for our next revision, we would set the flag deployment as its own system since it provides the most points. In addition to this, we also learned to take into consideration the possibility of anything that can go wrong within the field, including rare cases of friction between the rocks and the lunar ridge, as well as improper beacon alignment. Some advice we would give to future teams is to make interfaces adjustable, and as well as analyze the effects of system failure. Because we didn't take the time to account for this, we weren't able to seed higher, and we only placed 12th out of the 23 teams.